So, okay then, it's now officially pouring. So, what I did for this test, give you a heads up that for the 3 chapters, for those questions at the end, what I did is I took 2 homework questions from each chapter and threw them on your test. So you just have to see which one they would be. So I'm going to kind of, get that out. So remember you had a homework question about this? So it goes something like this, speed is distance divided by time, velocity has a direction component, and acceleration is change in velocity. So like I said, I'll post all of these. And remember that units of acceleration are meters per second squared. Okay, so that's a homework question. The next one, Newton's 3 laws of motion. Actually, I don't have them here on the review slide, but just like your homework, okay, be able to state and give an example for Newton's 3 laws of motion. And then we talked about mass versus weight, and mass is the amount of matter that's in an object, and weight has to do with gravity. So weight is the force created as gravity works on a mass. I see something I need to add to this slide. And then when it says visiting the moon, actually there is a homework question where, do you remember that on the moon you're going to have 1/6 of the weight? So 1/6, not 1/2. 1/6 of the weight. So like if you weigh an object that weighs 30 pounds here, 1/6 of 30 is 5. So it would weigh 5 pounds on the moon. Okay? So you'll have 1/6. Oh, yeah, let's go. But here's the catch, and I can't remember if the question on the test is like this. Your mass will be the same. Mass is same. I mean to say that if you're on the moon or if you're on Earth, your mass is the same. And then we talked about different types of energy, and kinetic and potential are oftentimes go together. So kinetic energy is associated with motion, and potential energy is stored energy. Sometimes we call it stored energy associated with position. I'll add that. Stored energy associated with position. And actually, in this last chapter, we're talking about chapter 6, kind of it's the potential energy, like the big cloud had lots of potential energy, small, not so much. So, and then the whole E is equal to mc squared. In that little Einstein equation, the m is mass, okay, and c is the speed of light, and it's very big. C is speed of light. Okay, so the thing is, since the speed of light is very big, if you square a real big term, it's a really big term. So a small amount of mass, speed of light squared. So the point here is that you get a large amount of energy from a small amount of mass. And that's actually what's going on with nuclear reactions, like as in the sun. And then Newton's law of gravitation actually was a homework question too, wasn't it? And the force of gravity is equal to G. G is that constant. And then you have 2 terms, m1 and m2. Those are the masses. And r squared, or r or d squared, is the distance between the 2 objects. Then angular momentum is like regular momentum. It has a mass term, a velocity term, and a radius term, though. So angular momentum is mass times velocity times radius. So that's why if your radius gets small, your velocity goes up. And then actually, I think the whole thing about tides, you also had a homework problem here. Okay, so tides are created by the gravitational pull of the moon. The neap tides are the diminished tide that happens at the quarters. And the spring tide is the higher, is unusual, especially high tide that happens at full and new moon. Mm-hmm. Better rain than snow.
Is things gonna cool things down? I don't. It's supposed to be
Hot tomorrow, isn't it? Yeah, you're right. The cold front comes through Saturday.
About Monday,
Saturday.
Saturday.
Mhm.
Yeah. I remember this one.
Yeah, I bet you do. So then up here I have the cousins: gamma rays, X-rays, ultraviolet, visible, infrared, microwaves, and radio waves. And then I kind of break out the visible into the colors of the rainbow. Remember how it goes is Roy G. Biv backwards, kind of as this is written, because red matches up with infrared and visible matches up with ultraviolet, or violet, excuse me, matches up with ultraviolet. Okay, and then with regard to the gamma rays, they have short wavelength, high frequency. And with regard to radio waves, they have long wavelengths and low frequencies. And then for all electromagnetic radiation, for all those cousins, for all those EM radiations, they all travel at the speed of light. So their velocity, which is actually the speed of light, is equal to the wavelength times the frequency for any given energy. Speed of light is the wavelength times the frequency. And then jumping on to the third term there, up here in the upper right-hand corner, I'm making an atom there. That's nucleus. We have protons and neutrons. Okay, and then we have electrons outside the nucleus. Okay, the symbol for electrons is E negative, protons P plus, neutrons N superscript 0. And then you know you have an ion if you have an atom that has lost or gained electrons. Okay, that's what an ion is. So if it loses electrons, it makes it positively charged. If it gains electrons, it makes it negatively charged. But put another way, I'll put this next to ions. A neutral atom, oops. I'm going to say number of protons equals number of electrons. And then for isotopes, they are atoms of the same element, so they have the same number of protons in their centers, but they have different number of neutrons in their centers. That's what an isotope is. Because the number of protons say what element it is. So speaking of the number of protons, then the next line there, atomic number is the number of protons. Atomic number is the number of protons. Okay? And then atomic mass number, you have to count number of protons plus number of neutrons. And then the next two kind of go together, electrons transitioning and the different type of spectra. So I drew a few diagrams over here. Okay, so this one, I drew 3 different energy levels. Okay, and I'm showing that little dot is an electron. I'm showing that electron go up. Okay, and notice the green squiggle, it's taking in energy. Okay, in this case, actually, when it sucks up energy, it creates absorption spectral lines. Okay? It's funny, I have absorption linen spectra. So, anyway. So that's that second one there. And then I have another scenario next to it where, again, I have 3 energy levels. Okay, but in this case, I'm showing an electron, that's a little blue dot, actually going down. And as it goes back down, it's emitting energy, And actually that will create emission line spectra. So those are your two types of spectra. And it's also showing electrons transitioning. Ways in which light interacts with matter have some possibilities. Light can be emitted, light can be transmitted through the matter, light can be absorbed, or light can be scattered or reflected. You gonna stop this rain, Jay? There's 4 ways. And then I love the next topic, the whole stars being different colors and being different temperatures. So blue stars are hotter, red stars are cooler, okay? The other thing about anything that's hot, like a blue star, it's already going to be brighter. Its intensity is going to be higher, okay?
That's kind of backwards, isn't it? Because we would think red
I've-
hot.
Yes, I've heard other students say that. It's
Cool.
like, for me, I've been teaching this so many years that I'm like, oh no, but you're right, when you say red hot, but white hot, usually white hot, so. And then if it's cool, not only will it be the longer wavelength, but also it'll be dimmer, okay? That's actually kind of the 2 laws of radiation there. And then the Doppler effect, how it works. So basically, you need to have motion between the observer and the source. So actually, I think your test question goes something like this. Well, what if, in class I kept saying, well, the source is moving towards you. Well, what if you're moving towards the source? You're also going to see a shift too. And so more generally in green down here, I just said it has to be motion between the observer and the source. Because you would see a Doppler effect if you were moving too. And then I noticed that in red I said, I don't think it's on the test, but not only do you have motion, but that motion has to be along the line of sight, which is called radial motion. So then the 2 types of motion, there's the blue shift, which is moving towards the source and observer, or moving towards each other, okay? And that shortens the wavelength. And then there's the red shift, where they are moving away from each other, and it lengthens the wavelength. And then 2 types of telescopes, refracting and reflecting. And all I did was focus on refracting telescopes use lenses and reflecting telescopes use mirrors. So like the one I brought in was the reflecting telescope. But like the Clark that you looked through was the refracting telescope, the observatory. And the Ealing was the reflecting telescope. And hopefully when you make it out to the observatory, you'll see those 2 telescopes. So it said, Mitchell made it out to the observatory. Mm-hmm. And Susan's thinking of going to the observatory, so.
I'm just like,
Yeah.
this is really gonna be tough, so I'm
Yeah.
concentrate on this, so.
Yeah. I'm not holding you to it. I just kind of make a conversation.
I
but-
thought about it after, yeah.
Yeah, and you know what? You've got a while too to get it in there. Yeah.
And
Yeah.
is there an observatory for the eclipse?
There's no observatory I'm going to be at the observatory for the eclipse, so you could come out then too.
On a Sunday?
On a Sunday, yeah.
What
So,
time?
the eclipse is at
It's at
9:30.
9:30.
Yeah, I'm going to probably set up by about 8.
Okay.
So, because I can. It's a fun place to be anyway.
That might work out better.
Okay, Sunday night, the 27th. Cool. I don't know. So the radio astronomy gets problematic because those wavelengths are so darn long. So you either need a humongous telescope, like we saw that one that was like 3 football fields long, humongous dish to catch the large waves, and or you need to have multiple dishes that are catching a segment, and then you put them all together, interferometry. Radio astronomy. So chapter 5 is just, oh my gosh, really? 10 billion things. I like it when you see the thing shake. You're like, a little bit of vibration there.
What's that? The bottom read.
This
the
one?
First of that, or.
And or more than
And or,
one.
and or.
Yeah, and or. Okay, so last chapter looks like this. Okay, so this should be kind of familiar. So where did Earth's water come from? I loved the video. I hadn't seen that for a while, the whole description of comets, but it was during that crazy period after Neptune like shook things up, and I loved it. So where did Earth get its water from? Comets. The next one, what was the solar nebula made of? And so this is actually a figure from your textbook. Okay. And I'm adding a term where it says frost line. Notice I put a little bullet out there. Actually, I think I'm going to probably amend this and post it out there and add the term frost line, because I think that's on your test, frost line.
And that goes with the.
Frost line is between Mars and Jupiter. And then actually frost line I have over here kind of separates what condenses, what frost line kind of separated things that were too close to the sun. Only like the rock and metal could condense where it was that hot. The hydrogen containing compounds needed to go to the cooler region. So frost line actually I think is on the test. Then I think I go on to the next term, conversion of gravitational potential energy. So actually I brought in a figure from your textbook that looks like this. Okay, so this actually is a figure we looked at tonight, where kind of from left to right is how our solar system formed. Remember when it was big? This is the solar nebula over here. Has lots of gravitational potential energy, low thermal kinetic energy. It gets smaller and spins, you know. Saw that when I heard it. That's not good. So you guys want to just kind of quickly finish? Okay. Okay. All right. Then this is a table from your textbook that compares the terrestrial planets versus the Jovian planets. Okay. The formation of moons around the Jovian planets. This is, do you recognize this from, okay. So this is like the sun is in the center there, and there's Jupiter. It kind of has its own little kind of accretion going on for its moons. The term planetesimal, it just simply means like a pre-planet, basically. Okay? The next two terms go together, left over from the formation of our solar system, asteroids and comets. Asteroids, they differ by where they are right now anyway. Generally, the asteroids are inner objects. They're just rocky. The comets are outer objects, and they are rocky with an ice component. Dwarf planet. Okay, I basically said dwarf planet orbits the sun, and it's spherical, but it has not cleared its own orbit. And the asteroid belt is pretty straightforward. The asteroid belt is basically where the frost line is. The asteroid belt is are asteroids located between Mars and Jupiter. I know. And then exceptions within our solar system. Okay, the Earth's large moon and the backward rotation of Venus and Uranus. Okay, actually those can both be explained by early bombardment. And that's all I have. Woo. I don't think we were supposed to evacuate the building. That just doesn't seem logical to me.
The what?